Hi there, welcome back to the channel, and in today's video I will be teaching you about how to use a servo motor and how to control it. So a servo motor is kind of like a precision motor. It's moving from 0 to 180 degrees normally, very precisely, like so. So the first thing we need to take note of here is that it's got 3 wires. This is the SG90 servo motor, by the way. It's commonly used. So suppose we have this block which represents this motor. So it's got a brown wire, red wire, yellow wire. Okay, so B for brown, R for red, Y for yellow. So the brown wire is the ground wire. The red wire is the voltage wire. So for this servo motor, 5 volts is just fine for the operating voltage, but you need to refer to the data sheet of the servo motor you may have, because that may differ. And the yellow wire is the PWM wire. So it's like the information wire that tells the servo what angle to turn to, pretty much. That's that. So moving on. This servo motor operates on 50 Hertz. And we want to find the time period. So how do we get that? The inverse of the frequency will give time period. So in this case, 1 divided by 50 will give us a time period of 20 milliseconds. Or 20 times 10 to the power of minus 3 seconds. And now we know the total time period of this servo, how it operates. We now need to check how much of this time period do we need to move the servo to the angle that we want. So based on the data sheet, we know that 0.5 milliseconds corresponds to an angle of 0 degrees, and 2.5 milliseconds corresponds to an angle of 180 degrees. So now we know that, we need to kind of convert this into how MicroPython would see it. So we typically do it in this way for duty. Duty underscore, for completeness, this is like, whatever object you have, dot duty underscore U16, and you pass that value into here. So that would correspond to unsigned 16-bit integer. So 16-bit is 2 to the power of n, where n is the bits. So in this case we have 16, and minus 1 will give us usable bits. So 2 to the power of 16 minus 1 is 65,535. And now we need to kind of ratio that. So 0.5 over 20 times 65,535 will give us 1663, I believe, and 2.5 over 20 times 65,535 will give us 8,000. Sorry, my calculation was wrong here. This is 1,638. And here we have 8,191. There we go. So again, visualizing this is important. So I'll just draw you this for your sake here. So here we have 20 milliseconds. This is like 3.3 volts or whatever. And so here we have 0.5 milliseconds. That will give us an angle of 0 degrees. But if I was to extend this pulse like this to 2.5 milliseconds, we will get 180 degrees angle in return. So that's just to help you visualize this information, which I hope is helpful for you. So now the next thing we need to do here is to relate those two things. Those 16-bit values and the degree values. And we do that by using the straight line equation like this. So we have 0 to 180 degrees, I guess. Then we have the lower value of 1638 here, and the upper value of 8191. So as you might know, the gradient or the slope is equal to y2 minus y1 over x2 minus x1. So that's just like rise over run, basically, of this slope. So we just input the values here, upper and lower, upper and lower. So we'll have 8191 minus 1638 divided by 180 minus 0 equals m. Just like that, that's the slope. So now we kind of want to rearrange it, so we get y equals mx plus c. Like that. So c is the y-intercept here. So we do 6553 divided by 180 times x. X is this variable here. Plus, wait, no, this is plus 1638, the y-intercept here will give us y. So now we know the equation that we need to work with within MicroPython to give us the corresponding angle. So with that said, let's move on to MicroPython, okay, and start programming this.
Okay, I want to show you in today's video as well how to make your own library and class with MicroPython, because in previous video we used someone else's library and class, so I just want to show you how to make your own. So first we need to call in the necessary classes that we need within this class or library I should say, that we're making. So from machine, all we need is this. We need the pin and PWM class from the machine library. So here we're going to start making the class. Let's call it Servo. You can call it what you want, of course. And here we're going to make a function, but it's a special type of function. We're using underscore underscore init underscore underscore. This is called like the initializer method, and what this does is like to, if you will, initialize the attributes of your object. So in this case we're working with a servo motor. So by the way, for whatever function you make within your class, you always need to call in self like this. So self and pin number. So we do self.pin will be equal to the pin number that we pass in here. Self.pwm is equal to PWM of the pin of the self.pin, just like that. And we next define the frequency of the PWM as we know it. Frequency is 50 Hertz. Oops, I don't know why I typed all that. You just do this. Frec. There we go. Oops. There we go, 50 Hertz. Now we make another one here, another function, if you will. Call it angle. You pass in self and the angle. Right, so self.pwm value will be equal to the equation that we derived earlier. You know it. So here we start by doing integer because we want this just to be a whole number. open bracket 6553 divided by 180 multiplied by x, or in this case the angle, and now we add in the y-intercept of positive 1638, just like that. Then we do self.pwm.duty cycle of an unsigned 16-bit integer, and then we pass in this self.pwm underscore value. So now that's all ready to go. One more step is you have to save it to the device that you're using. So save, and in this case I'm using the RP2040 device, so save it there. And let's call it Servo 1. Okay, now we can make a new file here, and now we can call it in. So from Servo 1 import servo, from machine import pin and ADC. We need ADC because we're going to use a potentiometer as well. So let's start by defining the servo pin. Servo pin equals, we're going to use pin 15, and here we go. Now we're going to do the ADC for the pin, other pin, pot pin equals ADC pin 26 is what we're going to use because that's a specified ADC pin on the Raspberry Pi Pico. And now we're going to make a function here, update angle, let's call it that, and we're going to pass in the pot pin value. So first we're going to read that value, pot r, pot pin dot read unsigned 16-bit integer like this. Then pot val, or we can call this angle actually. And then we do pot r minus 65. Wait, no, like this. This is the minimum value that I've found out by trial and error of using my potentiometer. If you want to find your minimum value, you just want to do line 6 and line 9, and then do a print of the final value that you get from line 9. So print pot r, and you will turn your potentiometer all the way down, and you should see the minimum value that you need to work with for your potentiometer. Okay, so 65,535 minus 288. Then we want to put all this in brackets and multiply at 180 because that's the range that we want it to be in, 0 to 180. And then that's done, return the angle. Okay, and while this is true, motor equals servo, servo pin. Angle is equal to update angle of pot pin. And motor dot angle, angle. So we've passed in the angle into the angle function within the class, and we've passed in the servo pin to the servo class like this. So now that's ready to go. Let's wire up the circuit and have a look at how it works. Okay, so here's the circuit that I've wired up on the breadboard here. I'll just walk through it with you quickly. So these are the 3 pins, the 3 wires of the servo motor. So the yellow is the PWM, the green is the 5 volts, and the blue is the ground. So you can see here's the 5 volts, here is the ground, and here's the PWM on GP15 of the Pi Pico. Here's the potentiometer. So orange wire goes to GP26, the ADC pin. The black wire goes to ground next to it. And this other blue wire here is 3.3 volts. So as you can see it here, when I turn this potentiometer, I turn the motor like this. Cool, right? But look, here's the oscilloscope.
So I don't think I mentioned this last time I showed you this, but what this oscilloscope shows you is the voltage against periods of time, and you can set the time base. So each grid here is right now equal to 1 millisecond. So if you take a closer look, this width of the pulse is half the box, so half a millisecond. But let's see it. Let's see when it's 2.5 milliseconds, according to our calculations. So when I turn this all the way, so it won't go up anymore. There we go, 2.5 milliseconds width of the pulse. You can see it you can see how this changes when I turn this. And that changes the angle here as well of the servo motor. So if you're wondering about how I wired this up to the oscilloscope, this is the probe that we use to take measurements. I've connected the red wire here as an output from GP15 also, and this brown wire goes to ground to complete the connection to give us this measurement of what we want. Okay, so yeah, that's all I have for today's video. This is how to control the servo motor using a potentiometer, and I showed you how to make your own libraries and classes within MicroPython. Okay, thank you very much for watching.